And now, another informative video from the NASA archives.
Here on Earth, the force of gravity is constantly acting to tip the gyroscope over. So it's not necessary to apply a torque, as Jerry Carr did with his straws. The rotation that we see here is precession. As the gyro slows down, it has less stability, and also the precession rate speeds up. As it slows down, we can also see its axis tip lower and lower, closer to the horizontal. In space, Jerry was able to demonstrate precession without these pivots, which have a lot of friction, and his gyro therefore maintained a steady speed unless it was disturbed. Now let's take a look at the precession of a larger double gimbal gyro. The friction of these gimbals and pivots is so small that this gyro behaves more nearly like the little gyro in Skylab. I'd like to emphasize that the motions of gyroscopes are straightforward consequences of Newton's laws of motion as applied to rotating bodies. But the precise explanation is a little too involved to get into now. But in brief, we can say that the stability of a gyro or other rapidly spinning rigid body is a consequence of its angular momentum. The law of conservation of angular momentum states that an external torque is required to change either the magnitude or the direction of the angular momentum vector. When you change the direction of angular momentum of a spinning gyro, it precesses, or it rotates slowly, in the direction of the applied torque, which is perpendicular to the applied force. Here a torque is provided by pushing against the gyro, as Jerry did in Skylab, or by the steady force of a weight. I hope you noticed that the gyro precessed faster with the heavier weight. Let's take another look at the precession of our little gyroscope in space.
Now, let's slow this thing down just a little bit more. I'm going to try to slow it down so slow that you could almost see the spokes going. You have to be careful not to touch it or you'll end up either tumbling it or with a handful of gyro. All right, now it's going so slow you can almost see the spokes go around. Now, let's tip it again. This time I'm going to try to tip it forward. If I want to tip it down, I need to push here, which means I want to put a force on it. Like so. The spacecraft systems, the Apollo system uses a little gyro like this, a set of them, and it uses these gyros to remember its orientation. What we do is before we spin up the gyro, we set it in a direction, set the axis in the direction that we want to have it go in, and we spin up the gyro with our electric motors, and then that gyro stays there, and it remembers where it is, and anytime our spacecraft drifts away from that attitude, the gyro tells the computer commands the thrusters to maintain our attitude. Now, in the case of Skylab, we also use little gyros like this to remember our attitude. However, when they feed their information to a computer, the computer then feeds information to 3 huge gyros. And the 3 huge gyros that we have that maintain the attitude of our spacecraft are 22 inches in diameter. They weigh 140 pounds apiece. The rim thickness right here is about 4 inches. And the speed at which our gyros operate is about 9,027 revolutions per minute. So essentially, the computer sends torques to this big gyro and puts pressure on it. And so the big gyro being connected to our spacecraft precesses and moves our spacecraft in the way we want it to. So, in review, we apply torques to the big gyros, and the big gyros apply a torque to the spacecraft to maneuver it to the position we want it to.